over decades. Malaria has become a huge burden to the world, especially countries like Africa. At night, female Anopheles mosquito, the vector who carries the malaria parasite, flies out searching for its blood meal. People who live in rural areas more often get bitten by this mosquito, and at the same time, mosquito finds a new host to inoculate the Plasmodium parasites. This is how the malaria parasite spreads, making thousands of people as victims of the malaria threat. This is not a threat which occurred overnight. Although prevention is better than cure, instead of prevention, people have get used to treatment. As humans, we had the privilege to have these precious antimalarial treatments. But have we wise enough to use them responsibly? With the increasing malaria cases, overuse of these drugs have led increase of emerging resistance within the Plasmodium parasite, making the wonderful drugs useless.
During the erythrocytic cycle, Plasmodium falciparum invades RBC and lives by ingesting hemoglobin from the RBC cytosol up to the digestive vacuole of the parasite. Hemoglobin degraded into peptides and heme. Then toxic heme converted into hemozoin within the digestive vacuole. Chloroquine is a diprotic weak base and it has charged and uncharged forms. Only uncharged molecule is membrane permeable. It freely diffuses into the erythrocyte up to the digestive vacuole of the parasite. Then chloroquine molecule become charged and trapped in the digestive vacuole due to charged chloroquine molecule is not permeable to the membrane. Then accumulated chloroquine molecules bind to hematin, a toxic byproduct of hemoglobin proteolysis and preventing its incorporation into the non-toxic hemozoin. Toxic free hematin cause lysis of parasite membranes leads to parasite death. Point mutation in the gene encoding PFCRT protein in the parasite. PFCRT is localized in the digestive vacuole membrane and allow the positively charged chloroquine molecules exit from the vacuole. Resulting decrease of chloroquine concentration inside the digestive vacuole cause reduction of the action of chloroquine. During the erythrocytic cycle, atavaquone competitively inhibits cytochrome BC1 complex of the parasitic mitochondrial electron transport chain. Inhibition of BC1 activity results loss of mitochondrial function. Resistance to atavaquone develop rapidly. CYTB gene encode to cytochrome BC1 complex. Point mutation at 268 codon of cytochrome BC1 gene mediate to atavaquone resistance.
These compounds contain endoperoxide bridges which are essential for antimalarial activity. Artemisinin is believed to act via a two-step mechanism. Artemisinin is first activated by intraparasitic heme ion which catalyzes the cleavage of this endoperoxide. A resulting free radical intermediate may then kill the parasite by alkylating and poisoning one or more essential malarial proteins. Artemisinin resistance typically refers to a delay in parasite clearance in blood. Currently only the ring stages of the parasites show the resistance. Therefore still artemisinin resistance is a partial resistance. Single point mutation in the Kelch13 gene usually causes this resistance. This causes for an increase of unfolded protein pathways which mitigate the protein damage caused by artemisinin action, leading to a resistance against artemisinin. Two key enzymes of folate synthesis of the malaria parasite are targeted by the antifolate antimalarial drugs. They are dihydropteroate synthase and bifunctional dihydrofolate synthase thymidylate synthase enzymes. Dihydrofolate synthase catalyze the conversion of para-aminobenzoic acid to dihydrofolate. This enzyme is competitively inhibited by sulfur drugs like sulfadoxine, dapsone, which are structural analogues of para-aminobenzoic acid. The bifunctional enzyme catalyzes the biosynthesis of DTMP by thymidylate synthase activity and the reduction of dihydrofolate into tetrahydrofolate by dihydrofolate reductase activity. This enzyme is inhibited by drugs like pyrimethamine and cycloguanil. Point mutation of the PFDHPS gene whose transcript dihydropteroate synthase makes the parasite resistant to sulfadoxine and dapsone. Point mutation of the PFDH-FTTS gene whose transcript bifunctional enzyme makes the parasite resistant to sulfadoxine and dapsone.
Decreased host immunity, AIDS, malnutrition, nonspecific immune response of non-immune individuals, recrudescence or drug resistance infection, overall drug pressure, inadequate drug intake, drug interactions, pharmacokinetic and pharmacodynamic properties of the drug. Reduce overall drug pressure by improved diagnostic methods. Reduce exposure of subtherapeutic blood level of the drug to parasite. Improve the way of drug usage by directly observed therapy, combination therapy, such as artemisinin-based combined therapy.